You're sitting inside a room, and most of that room is empty. Between you and the far wall there is mostly nothing, just a little air and a lot of open space. And yet that empty space, according to our best and most carefully tested theory of matter, is not empty at all. It is filled with restless energy, and when physicists add that energy up, they get a number so enormous that the universe should have been crushed to a point or torn to shreds long before you were born. The prediction misses reality by a factor with roughly 120 zeros after it. That gap has a name, the cosmological constant problem, and over the next couple of hours we will build up to it slowly, one plain step at a time. If you enjoy a patient walk through a real mystery, take a moment to subscribe. How can empty space weigh anything at all, and why are we still here to wonder about it? Look across the room you're in right now. Near the floor there is a chair, maybe a table, the solid things you can knock on. But most of what fills the room is not solid at all. It is the space between those things, the gap your hand sweeps through when you reach for a cup. We call that gap empty, and for most of human history that word meant exactly what it sounds like. Empty meant nothing there. No stuff, no weight, no story worth telling. The ancient Greeks argued about this without any instruments at all. Some, following Democritus, said the world was made of tiny hard pieces moving through a void, and the void was pure absence. Others, following Aristotle, could not accept a true nothing, and insisted that space must always be filled with something. That argument sat unsettled for 2,000 years, because no one could reach into empty space and check. When physics finally learned to check, in the last century, it found something that neither side quite expected. The empty space in your room is not a passive stage where objects act out their lives. It is doing things. It has energy of its own, a faint restless activity that never switches off, even when every particle of matter is removed and the temperature is dropped as low as the laws of nature allow. That claim sounds like a trick of words, so hold on to your ordinary picture for a moment, because it is a good one. When you pull the air out of a sealed jar with a pump, the inside really does become emptier. The hiss fades, sound no longer carries, a feather inside would fall like a stone. In every way you can test with your hands, that jar holds less and less. Your instinct that emptiness means absence is earned, and it is correct as far as it goes. The trouble begins when we push past what the hands can feel and ask what remains in that jar when the very last atom is gone. The honest answer, the one our deepest theories give, is that something remains. Not matter, and not heat in the usual sense, but energy woven into the fabric of space itself. Physicists call it the energy of the vacuum, and the vacuum here does not mean a machine or a jar. It means space with everything taken out. This is where the story we're going to follow begins, and it begins with a mistake. Not a small slip in arithmetic, but the largest gap between a prediction and a measurement that physics has ever produced. When we take our best theory of how the tiny world works and ask it how much energy sits in that empty jar, it hands back a number so large that space, weighed down by it, should have curled up or blown apart almost the instant it formed. The universe you're sitting in should not exist, or at least not in any form that could hold a room, a chair, and a person wondering about it. And yet here you are. The universe is calm, wide, and old. So either our best theory is wrong in some deep way we have not found, or something we do not understand is quietly holding that enormous energy in check. We are going to build up to that gap slowly and fairly, the way it was actually discovered, one careful step after another. To get there, we first have to earn a few plain ideas. We need to know what a field is, why the quantum world can never be perfectly still, and how empty space came to have any energy at all. Each of those will rest on the one before it. For now, only carry this single thought out of the room with you. The emptiness around you is fuller than it looks. To understand the energy in empty space, we first need a plain idea of what a field is, and the best place to meet one is on a kitchen table with a magnet and some iron filings. Take a bar magnet, lay a sheet of paper over it, and scatter fine iron filings across the paper. Tap the sheet gently. The filings do not lie where they fall. They gather into curved lines that arc from one end of the magnet to the other, thick and crowded near the poles, spreading out and thinning in between. You have seen this picture in a school book, and it is worth pausing on because you are looking directly at something invisible. The filings are not the field. They are just tiny compass needles, each one turning to point along a force that was already there in the empty space above the magnet before you scattered anything. Lift the filings away and the arrangement they revealed is still present. Every point in the space around the magnet has a direction and a strength built into it, a readiness to push or pull on anything magnetic that arrives. That readiness, spread smoothly through space, is what we mean by a field. The man who first took this picture seriously was Michael Faraday, a bookbinder's apprentice in London who became one of the greatest experimenters who ever lived. Faraday had almost no mathematical training. He thought in pictures, and the picture he trusted was exactly the one the filings draw. He imagined lines of force reaching out from magnets and electric charges, filling the space around them, real as ropes. Most physicists of his time found this childish. They believed in forces that leapt across empty space from one object to another, instantly, with nothing in between. Faraday's insistence that the in-between was where the action lived struck them as a craftsman's fancy. He was right, and they were wrong, and the difference matters for our whole story. If forces simply jump across a true nothing, then empty space is still empty, a mere distance to be crossed. But if the space around a magnet is genuinely altered, genuinely holding a pattern of push and pull at every point, then empty space is not nothing. It is a thing with structure, a medium that can carry a condition. Think about what the field does even when nothing is there to feel it. Bring a second magnet slowly toward the first, and you feel resistance building before the two ever touch, growing stronger as they close. That resistance was waiting in the space between them. The field held it, ready, whether or not you chose to test it. A region of apparently empty space was quietly loaded, like a drawn bow that no one has yet released. Faraday could not calculate the field, but he could feel his way around its shape through hundreds of patient experiments. He mapped how electricity and magnetism reached into space, how a moving magnet could stir an electric current in a nearby wire without any contact at all. Each result pointed the same way. The space around charges and magnets was active. It was full of a condition that could be shaped, stored, and passed along. We will lean on this idea again and again, so let it settle in plain terms. A field is a quantity that has a value at every point in space. The magnetic field has a strength and a direction at every point. So does the electric field. Later we will meet fields for other things too, and even fields whose ripples we call particles. But the first and simplest lesson is the one that iron filings teach. What looks like empty space above a magnet is not empty. It is filled with an invisible pattern that is ready to act. That pattern was still just a picture in Faraday's mind. It took another man, armed with equations, to prove the field was real and to show it could carry light itself. The man who turned Faraday's pictures into hard mathematics was James Clerk Maxwell, a Scottish physicist with a gift for seeing the deep unity under messy facts. Maxwell read Faraday's experimental work closely and did something remarkable. He took the craftsman's lines of force, which serious theorists had dismissed, and wrote them down as precise equations that any physicist could test. By the 1860s, Maxwell had gathered everything then known about electricity and magnetism into a small set of relations. In plain words, they say how electric fields are made by charges, how magnetic fields curl around currents, and how a change in one field creates the other. That last part is the seed of everything. A changing electric field produces a magnetic field. A changing magnetic field produces an electric field. Each one, by changing, gives birth to the other. Maxwell saw what this loop allowed. Imagine an electric field that suddenly shifts. It creates a magnetic field nearby. But that new magnetic field is itself changing as it grows, so it creates an electric field a little further along. That electric field is changing too, so it creates another magnetic field beyond it, and so on. The disturbance does not stay put. It hands itself forward through space, electric to magnetic to electric, a self-renewing ripple that carries on with no charges or magnets needed to keep it going, a wave in the field feeding itself as it travels. Then Maxwell did the calculation that made physicists sit up. His equations set the speed of that self-renewing wave, and the speed came out to a specific number fixed by two quantities measured in ordinary laboratory experiments on electricity and magnetism. When he worked out that number, it matched the measured speed of a light almost exactly, about 300,000 kilometers every second. That match was not a coincidence, and Maxwell knew it at once. Light was the wave he had found. Light is a ripple in the electric and magnetic fields, moving through space at the speed his equations demanded. The warmth you feel from the sun, the colour of the sky, the glow of a screen, all of it is the electromagnetic field vibrating and carrying energy from one place to another. What Faraday had drawn as lines, Maxwell had shown to be a real, physical medium that could hold waves and send them across the room and across the void between stars. Notice what this does to empty space. Sunlight crosses 93 million miles of near-perfect vacuum to reach your face. There is no air out there to carry it, no rope, no wire. If empty space were truly nothing, light could not make the trip. It crosses because the field is there, in the emptiness, able to vibrate. The vacuum between the sun and the earth is not a passive gap. It is the very thing the wave rides on. So the field passed from a picture in one man's mind to a proven feature of the world. Space around us is threaded with the electromagnetic field, and that field can carry energy in the form of light. Energy you can measure the moment sunlight warms your skin. Faraday's stubborn intuition had become the most successful physics of its century, uniting electricity, magnetism, and light into a single elegant scheme. But Maxwell's field was still a smooth thing, a continuous quantity that could ripple as gently or as fiercely as you liked, carrying as little or as much energy as you cared to give it. That smoothness felt obviously right for over 30 years. It was also, in a way no one saw coming, the next thing that would have to break. The field would keep its reality, but the idea that its energy could come in any amount at all was about to fail, and the failure would open the door to the quantum world. Before we step into the quantum world, we should be clear on one plain point, because the whole mystery ahead turns on it. A field does not just push and pull, it holds energy, real energy, the kind you can collect, store and spend. You already trust this with your body. Stand in sunlight and your skin warms. That warmth is energy that crossed empty space as a ripple in the electromagnetic field and arrived at you. A green leaf takes the same field energy and locks it into sugars. A solar panel takes it and pushes a current through wires. In every case the ledger balances. Energy left the sun, rode the field across the void, and did work when it arrived. The field was the carrier, and what it carried was real. The energy is not only in the travelling waves, it sits in a standing field too, in a field that is just holding still. Charge up an ordinary capacitor, two metal plates with a gap between them, and you have stored energy in the electric field in that gap. Let the plates connect through a bulb, and the stored field energy flows out and lights the room for a moment. Nothing crossed the gap but the field's own condition, yet the energy was there, waiting in the space between the plates, ready to be spent. Physicists learned to write this down precisely. Every point in space where a field has some strength holds a little energy, and the stronger the field at that point, the more energy sits there. Add up those little contributions across a region, and you get the total energy stored in the field throughout it. A strong field means a lot of energy packed into space. A weak field means a little. Zero field means, in the ordinary picture, zero energy. That last line is the one we'll have to revisit later, so keep it in view. Consider how much energy a field can hold when it is strong. The magnetic field of a large research magnet can grip tons of steel. The electric field in a thundercloud builds until the air itself gives way in a bolt of lightning, releasing in an instant the energy the field had gathered over minutes. These are not gentle effects. The field is a genuine reservoir, and when it discharges, you feel it as heat, light, and force. So the emptiness around us can carry energy in two ways at once. It can hold energy in a standing field, like the charged gap in a capacitor, and it can pass energy along in a travelling wave, like sunlight. In both cases, the energy lives in the field, spread through space, not in any solid object. If you could somehow measure the total field energy in a region and found it was not zero, you would have to conclude that the region, however empty of matter, was not empty of energy. That is exactly the situation we are marching toward. Everything so far has been the calm, well-tested classical picture, the physics of Faraday and Maxwell, and in that picture empty space with no fields present holds no energy at all. Remove the charges, remove the magnets, let every wave pass on by, and the ledger reads zero. A true vacuum, in classical physics, is genuinely empty and genuinely weightless. The quantum world is about to overturn that last comfortable line. It will agree that fields carry energy, and it will agree that a strong field carries more than a weak one. But it will refuse to let any field, anywhere, sit at exactly zero and stay there. And once a field can never be perfectly still, empty space can never be perfectly empty. To see why, we have to leave the smooth classical picture behind and meet the strange rule that the tiny world runs on, the rule that energy itself comes in grains. At the very end of the 1800s, physics ran into a small, stubborn problem about glowing objects, and solving it cracked the whole world open. The problem was the colour of heat. Everything warm glows. A poker in a fire goes from dull red to orange to yellow-white as it heats. Physicists wanted to predict, for a given temperature, exactly how much light of each colour a hot object should give off. Using the smooth field picture we have built so far, treating light as waves that could carry any amount of energy at all, they got an answer that was not just wrong, but absurd. Their equation said a warm object should pour out an infinite amount of energy at the blue and violet end of the spectrum. A quiet coal in a grate should blast the room with a lethal flood of ultraviolet. Since fireplaces plainly do not do this, something in the reasoning was broken. The man who found the fix was Max Planck, a careful and rather conservative German physicist who did not enjoy overturning things. In 1900, working almost in desperation, Planck found that he could match the real glow of hot objects perfectly if he made one strange assumption. He supposed that light could not carry just any amount of energy. Instead, for light of a given colour, energy could only be given out in whole multiples of a certain smallest amount, a little indivisible packet. Half a packet was not allowed. Energy came in grains. The size of that grain depends on the colour of the light, and the two are tied together by a number Planck had to introduce, now called Planck's constant. It is a very small number, which is why we never notice the graininess in daily life. The packets of ordinary light are so tiny that a lamp pours out billions of them, and the stream looks perfectly smooth, the way a beach looks smooth from a distance, even though it is made of separate grains of sand. Only when you get down to single atoms and single packets does the lumpiness show. Planck himself was uneasy. He treated his energy grains as a mathematical trick, a bookkeeping move that gave the right answer, and he hoped someone would later explain them away. But the grains were real. A few years later, Albert Einstein took them seriously and showed that light striking a metal knocks electrons loose only in a way that makes sense if light truly arrives as discrete packets, each one delivering its whole grain of energy at once or not at all. Those packets are what we now call photons. Einstein received the Nobel Prize for that work, not for relativity. This is the birth of the quantum, and the word itself just means a fixed amount, a quantity that comes in units. The lesson is that the smooth, continuous field of Maxwell was an approximation, beautifully accurate for large, gentle waves, and wrong in the fine grain. Down at the smallest scale, the electromagnetic field does not ripple by any amount you please. It changes in steps, packet by packet, grain by grain. Hold that idea beside what we said about field energy. A field stores energy, and now we learn that this energy is not smooth but lumpy, parcelled into grains whose size is set by Planck's constant. That may sound like a small technical correction. It is not. Once energy is forced to come in fixed grains, a deeper rule follows close behind, a rule about how still a grainy quantum thing is allowed to be. The next step in our climb is that rule. It says that the tiny world can never hold perfectly still, and it was written down by a young man named Werner Heisenberg. It is the single fact that will fill empty space with energy and set our whole mystery in motion. In the 1920s, a young German physicist named Werner Heisenberg found a rule buried in the new quantum mathematics that unsettled even the people who discovered it. The rule sets a hard limit on how precisely certain pairs of things about a tiny object can be known at the same time. The most famous pair is position and motion. Here is the plain version. For a tiny thing like an electron, you cannot pin down both exactly where it is and exactly how it is moving. The sharper you know its position, the blurrier its motion becomes, and the sharper you know its motion, the blurrier its position. This is not a limit of our instruments, a matter of clumsy measurement that better tools would fix. It is a limit built into the nature of the thing itself. The electron simply does not possess a perfectly definite position and a perfectly definite motion at once. That is a strange sentence, so lean on a rough comparison. Picture trying to photograph a hummingbird's wing. If you use a very fast shutter, you freeze the wing and see exactly where it is, but the frozen image tells you nothing about how fast it was beating. If you use a slow shutter, you get a smear that shows the speed of the beat, but now the wing has no single sharp location. With the hummingbird, this is only a limit of cameras. In the quantum world, the blur is real. The wing genuinely does not have both a sharp place and a sharp speed to be captured. The comparison breaks down in an important way, and the break is the whole point. A hummingbird wing really does have a definite position at each instant, and a fast enough camera would prove it. An electron does not. The fuzziness is not hiding a sharp truth underneath. The fuzziness is the truth. Nature holds the two quantities in a kind of trade, and it will never let both go sharp together. Now follow where this leads for stillness. To be perfectly still is to sit at one exact spot with exactly zero motion. That is precisely the state Heisenberg's rule forbids, because it would mean knowing position and motion both perfectly at the same time, one nailed to a point and the other nailed to zero. The quantum world does not allow it. A tiny thing can never be caught fully at rest. There is always some residual jitter, some irreducible trembling that cannot be removed no matter how much energy you take away. This is where the emptiness in your room starts to fill. Cool a small object down. Take away its heat, slow it as far as it will go, drop the temperature toward absolute zero, the coldest anything can ever be, about 273 degrees below zero on the Celsius scale. In the old classical picture, a thing at absolute zero would sit perfectly frozen, motionless, with no energy of motion left at all. Heisenberg's rule forbids exactly that. Even at absolute zero, with every possible scrap of heat removed, the tiny world keeps a last flicker of motion that can never be taken away. That leftover flicker has a name we will use often. It is called zero-point motion, and the energy tied up in it is called zero-point energy. The energy that remains at the 0 point of temperature, when by every ordinary measure there is nothing left to give. We now have the two ideas the whole mystery needs. Fields carry energy, and quantum things can never be perfectly still. Put them together and something has to give. If a field is a quantum thing, then it too can never sit perfectly still, not even in empty space with nothing around. And a field that can never be still is a field that always carries some energy. To see that clearly, we need one clean, simple example of quantum trembling, and physics has a favourite. It is the humble spring. Physicists have a favourite toy for thinking about trembling things, and it is the simplest one imaginable, a weight on a spring. Pull the weight down, let go, and it bobs up and down. Give it a hard pull and it swings widely, carrying a lot of energy. Give it a gentle pull and it barely stirs, carrying little. Let friction drain it, and in the old picture it eventually stops, hanging motionless, with zero energy of motion. This bobbing system has a proper name, the harmonic oscillator, and it stands in for almost anything that vibrates, from a plucked string to an atom jiggling in a crystal. Now shrink the spring down to the quantum scale, and Heisenberg's rule takes hold. The tiny oscillator cannot hang perfectly still, because perfect stillness would mean an exact position, and exactly zero motion at the same time, and that is the very thing forbidden. So the quantum oscillator, even in its lowest possible state, even with every scrap of energy removed that can be removed, keeps trembling a little. It never fully stops. The mathematics of quantum theory makes this exact. The energy of a quantum oscillator comes in grains, just as Planck found for light, so it can hold one grain, or two, or three, stacked up like rungs on a ladder. But the ladder does not start at the floor. Its lowest rung sits a little above zero. Even in that lowest rung, the ground state, the oscillator holds a fixed amount of energy that it can never give away. This is the 0-point energy again, now made concrete. The floor of the ladder is not at zero. It is lifted permanently by half a grain. That half grain sounds trivial, and for one lonely oscillator it very nearly is. The energy is minute. But the reason this matters for our story is that fields, the electromagnetic field included, are made of oscillators. Not one, but a vast number. Here is the connection, and it is the hinge of everything to come. When Maxwell's field ripples, it can ripple at many different frequencies at once, a low slow wave and a high fast wave and everything between, all sharing the same space. Each of those possible waves behaves, mathematically, exactly like one of these little springs. A wave of a given frequency is a quantum oscillator, so the electromagnetic field is not one oscillator. It is an enormous collection of them, one for every possible wave that could exist, packed into every region of space. Follow the consequence slowly. Each of those countless oscillators, by Heisenberg's rule, must keep its half grain of 0-point energy, even in its lowest state, even when no light is present and no charges are near. Empty space is not empty of these oscillators. They are the field itself, and the field is everywhere. So every point in space carries the trembling of a great host of oscillators, each contributing its small, unremovable share of energy. Add them up, and empty space is humming with energy. Not because anything is there in the ordinary sense, no photons, no matter, no heat, but because the field that fills all space can never be truly at rest. Take a sealed box, pump out every atom, cool it to absolute zero, and shield it from all light. Inside is a perfect vacuum by every classical measure, and inside, according to quantum theory, the electromagnetic field is still trembling with 0-point energy at every point, quietly, unremovably. This is the moment the vacuum stops being nothing. The empty space in your room is filled with the restless ground state jitter of the quantum fields that live there. It is faint, it is invisible, and for a long time it looked like a harmless bookkeeping detail. To see how faint it should be, and how enormous it turns out to be, we first need to understand why physicists came to believe there is not just one field-filling space, but many. That story begins with Paul Dirac. In 1928, a quiet, precise Englishman named Paul Dirac was trying to do something that looked almost impossible. He wanted to write down an equation for the electron that respected two great theories at once: the quantum rules of the tiny world and Einstein's relativity, which governs anything moving near the speed of light. Dirac was famously sparing with words and famously deep with mathematics, and the equation he found changed how physicists picture reality. Dirac's equation worked beautifully for the electron, but it came with a surprise built in. The mathematics insisted that for every kind of particle there should be a partner with the opposite electric charge, a mirror twin. For the electron, that twin would be a particle just as light, but positively charged. At first this looked like a flaw. Then, a few years later, exactly such a particle was found in cosmic rays, the anti-electron, now called the positron. Dirac had predicted antimatter from the shape of an equation, and nature had it in stock. It remains one of the most striking cases of pure mathematics pointing straight at something real. But the deepest change Dirac helped bring was not antimatter. It was a new answer to a simple question. What is a particle? In the older quantum theory, an electron was a tiny thing that had a fuzzy position and a wave attached to it. Dirac and the physicists who followed him found something cleaner and stranger. They found that the right way to describe nature was to start with fields, spread through all of space, and to treat particles as ripples in those fields. Think back to Maxwell. He showed that light is a wave in the electromagnetic field, and Planck and Einstein showed that this wave comes in grains called photons. So a photon is not a little pellet flying along. It is a quantum ripple in the electromagnetic field, the smallest allowed disturbance of that field, 1 grain of it. Dirac's work extended this idea to matter. There is an electron field filling all of space, and an electron is a quantum ripple in that field, its smallest allowed disturbance. The positron is a ripple of the opposite kind in the same field. This is the heart of quantum field theory, the framework that grew from Dirac's work and became our deepest description of matter and force. In it, the world is not fundamentally made of particles moving through empty space. It is made of fields, one for each kind of particle, all overlapping and filling every corner of the universe. There is a field for electrons, a field for photons, fields for the particles inside the atom's core, a field for each type of thing that exists. What we call a particle is a knot of energy in one of these fields, a lump that the field's quantum rules allow. See what this does to our picture of empty space. If every particle is a ripple in a field, then the fields are there whether or not any ripples are present. A calm sea is still a sea even with no waves on it. Remove every particle from a region, and you have not removed the fields. You have only smoothed them down to their quietest state. And we already know, from Heisenberg and the trembling oscillator, that the quietest state of a quantum field is not perfectly still. It keeps its 0-point jitter. So the vacuum of quantum field theory is a place where many fields, not just one, are all sitting in their lowest trembling states at once. Every one of them, the electron field, the photon field, all of them, contributes its own 0-point energy to the emptiness. The humming we found in the last chapter is not the humming of one field. It is the combined hum of all the fields of nature layered together in every cubic inch of what we call nothing. That layered hum has a texture, and the next step is to look closely at it. Up close, the calm vacuum turns out to froth. It helps to give the emptiness a proper name and a proper definition, because we're going to spend the rest of this story weighing it. Physicists call it the vacuum state, and it means one specific thing. It is the lowest energy state that all the fields of nature can be in at once, not a place but a condition. When every field has settled as far down as it can go, when no real particles are present anywhere, that shared quiet is the vacuum. The word lowest is important and slightly misleading, so hold it carefully. The vacuum is the lowest the fields can go, but we have already seen that this lowest rung is not at 0. Each field, like the trembling spring, keeps its 0-point energy even in its ground state. So the vacuum is the floor, and the floor is raised. You cannot dig beneath it. There is no state of the world with less energy than the vacuum, and yet the vacuum still hums. One feature of this state matters more than it first appears. The vacuum looks the same to everyone. If you drift through empty space at a steady speed, the vacuum around you looks exactly as it does to someone standing still. It has no current, no preferred direction, no way to tell you which way is forward or how fast you're going. This sameness is not a small nicety. It is a strict demand of relativity, and it forces the vacuum's energy to have a very particular character. Whatever energy fills empty space must fill it evenly, the same in every direction, the same for every observer, with no texture that would let you find your bearings. That even, directionless energy, is the same thing Einstein would later handle in his gravity equations, and we will get there. For now, notice how odd it is. Ordinary energy usually comes with a direction. Sunlight streams from the sun, heat flows from hot to cold. But the energy of the vacuum just sits, uniform and still looking, offering no handle to grab. It is the calmest possible face on the most restless possible thing, and it is restless, underneath. The calm of the vacuum is the calm of an average, not of a truly quiet sea. Return to the picture of countless oscillators, one for every wave the fields can carry. In the vacuum, each of them is in its ground state, trembling with its half grain. On the surface, averaged over any patch large enough to see, it all looks smooth and empty. But at the finest scale, the fields are seething, dipping and rising, never holding still. Try to picture the surface of a pond on a windless day. From across the garden it looks like glass, flat and quiet. Kneel down and put your eye to the water, and you find it is never truly flat. It shivers with tiny ripples too small to see from a distance, a constant fine motion across the whole surface. The vacuum is like that pond seen up close, except the shivering can never be stilled, not by cold, not by shelter, not by anything, because it comes from the quantum rule itself and not from any breeze. Now the trouble starts to take shape. If every field in nature contributes its 0-point trembling to this vacuum, and if the trembling includes waves of every frequency, from long gentle ones to unimaginably short and violent ones, then the energy stored in that seething emptiness could be very large indeed. The smaller and faster the ripples we allow, the more oscillators there are, and the more 0-point energy they carry. To weigh the vacuum, we will have to decide how far down into those tiny furious ripples the trembling really goes. But before we count, there is one more thing to see in the froth, the fleeting particles that flicker in and out of the emptiness and leave real marks behind. The trembling of the vacuum does more than hum. It flickers with brief appearances of particles that come and go too quickly to catch. Physicists call them virtual particles, and understanding what they are and what they are not keeps the whole picture honest. Recall Heisenberg's rule, which we met for position and motion. There is a second version of it that trades energy against time. It says that over a very short stretch of time, the energy of a system is not perfectly fixed. The briefer the moment, the fuzzier the energy is allowed to be. Nature will let energy appear, so long as it vanishes again quickly enough, before any lasting ledger could record it. A large borrowing must be repaid almost instantly. A small one can linger a little longer. This loophole lets the vacuum do something remarkable. In empty space, for the briefest instance, the fields can borrow energy to conjure a pair of particles, say an electron and its antimatter twin the positron, which flicker into being and then annihilate each other and vanish, returning the borrowed energy before the moment closes. They appear in pairs, matter and antimatter together, so that all the ledgers of charge and other quantities still balance. They are born and gone so fast that you can never trap one or point to it. That is why they are called virtual. They are not steady, lasting things. They are the fleeting froth of the restless fields. It is tempting to dismiss this as a fairy tale, a way of talking that could never be tested. It would be fair to be suspicious. But the froth leaves fingerprints, real and measurable ones, and this is where the story earns its keep. The constant flicker of virtual particles subtly changes how real particles behave, and those changes have been measured to staggering precision. Consider a single electron sitting in empty space. It is not truly alone. It is surrounded by the vacuum's froth, a swarm of virtual pairs flickering around it, screening and tugging at it. This swarm slightly alters the electron's magnetic strength and slightly shifts the energy levels of electrons bound in atoms. Quantum field theory can calculate the size of these shifts by carefully accounting for the froth. When physicists compare the calculation to experiment, the two agree to more decimal places than almost any other prediction in all of science. The froth is not a story, it is there, and we can weigh its effects. So the vacuum, which looked like nothing, and then like a faint hum, now reveals a third layer. It is a sea of fields trembling in their ground states, and across that sea plays a constant fine froth of particles flickering into brief existence and out again. Emptiness, examined closely, is one of the busiest things in nature. There is a comparison worth holding, with its edge marked clearly. The vacuum is a little like the surface of boiling water, endlessly bubbling, forming and popping. But the comparison misleads if taken too far. Boiling water bubbles because heat is pouring in. The vacuum froths with no heat at all, at the coldest temperature nature allows, driven only by the quantum uncertainty in energy over short times. Take every scrap of heat away and the froth continues because it does not run on warmth. It runs on the same deep rule that keeps the oscillator trembling. We have now built the full, strange picture of empty space that quantum field theory gives us. Fields everywhere, never still, humming with zero-point energy and frothing with virtual particles that leave measurable marks. Each piece rests on solid experiment, and each piece adds a little more to the energy that empty space appears to carry. The natural next question is whether this energy pushes on anything, whether the vacuum's restlessness can do real, visible work. In 1948, a Dutch physicist worked out that it could, and he described an experiment simple enough to picture. 2 plain metal plates, and the vacuum itself squeezing them together. The Dutch physicist was Hendrik Casimir, working at the Philips Research Laboratory in the Netherlands. In 1948, thinking hard about the forces between molecules, Casimir realized that the zero-point trembling of the electromagnetic field should produce a small but genuine push, a force that comes straight out of the vacuum. He described a setup clean enough that we can picture every part of it. Take 2 flat metal plates, not charged, not magnetized, just 2 ordinary uncharged plates. Bring them very close together, facing each other, with only a tiny gap between them, far thinner than a hair. Casimir's claim was that the 2 plates would feel a force pulling them together, pressing them toward each other, with no batteries, no magnets, and nothing in the gap but vacuum. The empty space itself would push them. To see why, go back to the field between and around the plates, trembling with its zero-point waves of every frequency. Out in the open space beyond the plates, waves of all sizes can exist freely, but in the narrow gap between them, only certain waves fit. Just as a guitar string clamped at both ends can only sound certain notes, the waves in the gap must fit neatly between the 2 metal surfaces, so many of the possible waves are excluded, the ones that do not fit. Fewer allowed waves in the gap means less zero-point energy in the gap than in the open space outside. Now the vacuum behaves like anything else in nature. It settles toward the arrangement with the lowest energy. Since the gap holds less field energy than the surroundings, the plates are pushed toward each other, shrinking the gap, because closing them lowers the total energy of the field. The push is real, and it is directed inward, and it comes from nothing more than the difference in the vacuum's trembling inside and outside the gap. The force is astonishingly small. For plates about the size of a coin held a fraction of a hair's width apart, the push is roughly the weight of a small water droplet. This is why nobody had ever noticed it in daily life. At everyday distances, the effect fades away to nothing, and only when the plates come extraordinarily close does the vacuum's push grow strong enough to matter. The force climbs steeply as the gap narrows, so the last tiny distance is where the vacuum makes itself felt. Pause on what Casimir had done. He had taken the strangest idea in our story, that empty space carries energy in its trembling fields, and turned it into a concrete, testable prediction. If the vacuum energy is real, two neutral plates will attract by a specific, calculable amount that depends only on their size and their spacing, and on the fundamental constants of nature. If the vacuum energy is a fiction, the plates will feel nothing. There would be no room to argue. The vacuum would either push or it would not. This is the mark of physics at its best. A wild claim about the nature of emptiness had been sharpened into a yes or no experiment sitting on a laboratory bench. The 0-point energy stopped being a matter of interpretation and became a matter of measurement. There is a detail here that the common tellings often skip, and it is worth adding. Casimir first tackled this problem in a more complicated way, tracking the forces between individual molecules in the plates, and the mathematics was a thicket. It was the great physicist Niels Bohr, in a brief conversation, who nudged Casimir toward the cleaner idea that the whole effect could be seen as coming from the 0-point energy of the vacuum itself. According to Casimir's own account, Bohr mumbled something about 0-point energy, and that hint set him on the simpler and deeper path. Casimir published his prediction in 1948. Now it had to be tested. Measuring a force the weight of a dust mote across a gap thinner than a wavelength of light would take another 50 years and a great deal of experimental care. For decades, Casimir's predictions sat in an awkward place. Everyone agreed the effect should exist, and a few early experiments in the 1950s and 60s saw hints of a force of about the right size, but measuring it cleanly was brutally hard. The plates had to be smooth almost down to the atom, held perfectly parallel, and moved to within a fraction of a hair's width without ever touching. Any speck of dust, any faint electric charge left on the metal, any tiny tilt would swamp the delicate signal from the vacuum. The prediction was clear. The measurement was a nightmare. The breakthrough came in 1997, when the physicist Steve Lamoureux, then working at the University of Washington, measured the Casimir force with real precision for the first time. He solved the hardest part of the problem with a clever choice. Instead of struggling to hold two flat plates perfectly parallel, which is nearly impossible, he used a flat plate and a gently curved surface, a sphere, facing it. A sphere and a plate do not need to be aligned. They simply have a point of closest approach, and the geometry takes care of itself. Lamoureux mounted his surfaces on a sensitive torsion balance, an instrument so delicate it can feel forces far too faint for any ordinary scale, and slowly brought the sphere toward the plate. As the gap narrowed, he watched for the tiny inward pull the vacuum should produce. It was there. As the surfaces came within about a wavelength of light of each other, the force appeared and grew, following the steep rise Casimir's formula demanded, and the size of the push matched the prediction to within about 5%. Think about what that measurement means. Two uncharged pieces of metal, in a vacuum, at rest, were drawn together by a force with no source but the trembling of empty space. There was nothing between them to do the pushing, no field anyone put there, no charge, no current. The only thing in the gap was the vacuum, and the vacuum pushed, by very nearly the amount that the 0-point energy of the electromagnetic field said it should. In the years since, other groups have refined the measurement, using better instruments and finer control, and the agreement with Casimir's prediction has grown tighter, down to the level of 1% or so. The Casimir force is now a standard, reproducible fact of the laboratory. Engineers who build the smallest machines, devices with parts the size of a few thousand atoms, have to account for it, because at those scales the vacuum's push can make delicate parts stick together. So the strangest link in our chain is nailed down by experiment. The 0-point energy of the vacuum is not a bookkeeping fiction or a way of speaking. It exerts a real, measurable force that engineers must design around. Empty space carries energy, and that energy does work in the world. Now we can state plainly where we stand, because everything so far has been solid ground. Fields fill space. Quantum rules forbid them from ever being still. Their unremovable trembling stores zero-point energy in the vacuum. That energy froths with virtual particles whose fingerprints we measure to extraordinary precision, and it presses two plates together with a force we've weighed on a bench. Every step is confirmed. This is not speculation. This is some of the best tested physics we have, and that is exactly what makes the trouble ahead so sharp. The very same theory, the very same reasoning that gets the Casimir force right to within 1%, also tells us how much total energy should be packed into the vacuum. Not the small difference between the inside and outside of a gap, but the whole thing, the full weight of the trembling in every cubic inch of empty space. When we finally ask it that, and add the trembling up, the answer is wrong by more than 100 zeros. But first, we should see just how astonishingly right this same theory is elsewhere, so the size of the failure lands with full force. To feel the weight of the coming failure, you first have to see how spectacularly successful quantum field theory is everywhere else. The particular theory that describes electrons, photons, and their interactions is called quantum electrodynamics, or QED for short, and it is the most precisely tested theory in the history of science. When it is right to a degree that has no equal. Two measurements make the point. The first is a faint shift in the light given off by hydrogen, the simplest atom, a single electron bound to a single proton. In 1947, the physicist Willis Lamb, using techniques refined during the war, measured the energy levels of hydrogen more carefully than anyone before, and found that two levels which the older theory said should sit at exactly the same energy were in fact slightly split apart. This tiny gap became known as the Lamb shift, and the older theory had no room for it. Quantum field theory explained it exactly. The split comes from the vacuum's froth. The electron in the atom is constantly jostled by the trembling electromagnetic field and the flicker of virtual particles around it, and this jostling nudges its energy levels by a minute amount. When physicists calculated the size of that nudge from the theory of the vacuum, it matched Lamb's measurement. The froth we described earlier was not a picture for its own sake. It was doing measurable work inside every hydrogen atom, and the numbers agreed. The second measurement is even more stunning. Every electron behaves like a tiny magnet, and the strength of that magnet is a number you can both calculate and measure. A simple early theory predicted a certain value, but the electron sits in the vacuum's froth too, wrapped in its cloud of virtual particles, and that cloud slightly changes its magnetic strength. Quantum electrodynamics can compute the correction, term by painstaking term, following the flickers of the vacuum. The result agrees with experiment to about 12 digits. That is like measuring the distance from one coast of a continent to the other, and having your calculation and your ruler agree down to the width of a single human hair. No other theory in science reaches this kind of precision. When people say quantum field theory is our best tested description of nature, this is what they mean. 12 digits of agreement, again and again, in measurement after measurement, all of it depending on getting the behaviour of the vacuum and its virtual froth exactly right. The men who built this theory into its precise working form did so just after the Second World War, and their names belong in this story. Richard Feynman in America invented a way of picturing every interaction as a sum over little sketches of particles meeting and parting, which made the fearsome calculations manageable. Julian Schwinger, also American, built the same physics with heavier, more formal mathematics. In Japan, working in near isolation during and after the war, Shinichiro Tominaga had reached much the same result independently. The three shared the Nobel Prize for it. A young British physicist, Freeman Dyson, then proved that their different-looking methods were really the same theory in different clothes. So the picture is clear, and it is humbling. Quantum electrodynamics, resting entirely on the trembling, frothing vacuum we have described, predicts the behaviour of matter and light with a precision unmatched anywhere in human knowledge. It gets the Lamb shift right. It gets the electron's magnetism right to 12 digits. Every one of those triumphs depends on the vacuum being exactly what the theory says it is, which is why the next result is so hard to swallow. This same theory, this triumphant 12-digit accurate theory, when asked the simplest question about the vacuum, how much energy does it hold in total, gives an answer that is not just a little wrong. To understand that answer, we first have to face the infinities that the theory throws up along the way and the clever trick physicists use to tame them. There is a secret in the success of quantum electrodynamics, and physicists were, for a while, deeply uncomfortable about it. When you first try to calculate almost anything in the theory to full precision, following all the flickers of the vacuum, the sums do not give a neat number, they give infinity. The trouble comes from the froth itself. Recall that the vacuum trembles with waves of every frequency, including unimaginably short, fast ones. When you try to add up the effect of all those virtual flickers on, say, the electron's magnetism, you have to include waves of shorter and shorter wavelength, higher and higher energy, without any obvious place to stop. And as you push toward ever tinier, ever more violent ripples, the contributions do not settle down. They pile up without limit, and the answer runs off to infinity. A theory that predicts an infinite magnetism for the electron is, on its face, useless. For a while in the 1930s and 40s, this looked like it might sink the whole enterprise. The infinities appeared everywhere, and nobody knew how to make them go away honestly. The solution, worked out by Feynman, Schwinger, Tominaga and others, is called renormalization, and it is one of the strangest and most successful ideas in physics. The idea, stripped down, is this. The infinities always attach themselves to a few specific quantities, such as the electron's mass and its charge. Now, the mass and charge that appear in the raw equations are not things we ever measure directly. What we measure in the laboratory is the real electron, already dressed in its cloud of virtual froth, mass and charge and all. So renormalization says, in effect, take the measured values of the mass and charge, the finite numbers we actually observe, and use those to absorb the infinities. The infinite corrections get swallowed into the definitions of mass and charge, and once that is done, every other prediction the theory makes comes out finite and matches experiment to those 12 astonishing digits. It can sound like cheating, sweeping infinities under the rug by hiding them inside quantities we measure anyway. Feynman himself called it a dippy process, and was uneasy that it worked so well. But over time, physicists came to understand it more deeply. Renormalization is really an honest admission that our theory is only meant to describe nature down to a certain scale, and that we should not trust it to say what happens at infinitely small distances where unknown new physics may lurk. By folding the unknown short-distance behaviour into a few measured numbers, the theory makes reliable predictions about everything we can actually see, without pretending to know what happens infinitely far down. The important point for our story is that renormalization works by tying the infinities to measurable quantities and letting the measurements set the values. For the electron's mass, for its charge, for its magnetism, there is always some real, measured number to pin the infinity onto, and once pinned, it does no harm. The theory is saved, and it goes on to its 12-digit triumphs. But this rescue depends on there being something to pin the infinity to, some measured quantity that can absorb it. And here we arrive at the crack in the floor. There is one quantity in the theory where this trick has no natural anchor, one place where the froth piles up its energy, and there is no obvious measured number waiting to absorb the pile. That quantity is the total energy of the vacuum itself. When you try to add up the zero-point trembling of all the fields, overall frequencies, to get the energy density of empty space, you get the same runaway sum, climbing toward infinity as you include shorter and shorter waves. For every other quantity, renormalization gives you a way out. For the energy of the vacuum, the way out is far less clear, and what you're left with, once you make any reasonable choice about where to stop counting, is not infinity but something almost as troubling. A specific, enormous, and deeply wrong number. So let us finally try to weigh the vacuum and watch what the theory does. The recipe seems simple enough. Every field contributes 0-point energy, half a grain for each of its oscillators, one oscillator for every wave it can carry. To find the total energy in a patch of empty space, add up the half grains from all the waves, from the longest and gentlest to the shortest and most violent. The problem is where to stop. Long, gentle waves each carry only a little energy, and there are not too many of them, so they add up to a modest amount. But as we go to shorter and shorter waves, each one carries more energy, and there are vastly more of them able to fit into the same patch of space. The sum does not settle. The more we allow the tiniest, fiercest ripples, the larger the total grows, running upward without limit if we let the waves get infinitely small. Somewhere, physicists agree we should stop trusting the calculation. At some incredibly small distance, our current theories must break down and unknown physics must take over. The natural place to draw that line is a scale called the Planck length, built out of the fundamental constants of nature, the speed of light, Planck's constant, and the strength of gravity. It is fantastically small, so small that compared to it a single proton is as vast as the solar system is to a grain of sand. Below that scale, we simply do not know how nature works, so it is reasonable to stop counting the trembling there. Stop the sum at the Planck length, and you get a definite answer for the energy in every cubic centimetre of empty space. It is not infinity. It is finite, and it is staggeringly, absurdly large. The energy that quantum field theory says should be sitting in the vacuum, in the empty space of your room, comes out to a density so enormous that a single thimbleful would outweigh entire galaxies. Empty space, by this reckoning, is the densest, heaviest stuff imaginable, packed with more energy than anything made of matter. This is the leftover that renormalization cannot easily remove. For the electron's mass or charge, there was always a measured number to absorb the infinity. For the vacuum's energy, we could simply declare that we will measure the energy of empty space and define it to be whatever it is and subtract off the rest. And in a world without gravity, that is exactly what physicists would do, and no harm would come of it. Only differences in energy would matter, like the difference in vacuum energy inside and outside the Casimir gap, and those differences are finite and correct. The vast overall value would be a constant you could ignore, like the height of the sea floor when all you care about is the waves. But gravity does not let us ignore it. This is the heart of the whole problem, and it is worth stating slowly. In Einstein's theory of gravity, energy is what causes space to curve. Anything that carries energy, matter, light, heat, and yes, the energy of the vacuum itself gravitates. You cannot simply subtract the vacuum energy away and forget it, because gravity feels the total, not just the differences. If empty space really holds that staggering energy density, then empty space should gravitate with staggering force, and the shape of the entire universe should be ruled by it. So the harmless bookkeeping constant of a gravity-free world becomes, the moment gravity enters, a physical thing with enormous consequences. The trembling of the vacuum should weigh on space itself, and when we work out how much, and compare it to how much the real universe actually weighs, we find the largest disagreement between theory and observation ever recorded. To see why this disagreement is so devastating, we need Einstein's gravity, and we need to understand how the vacuum's energy connects to a single term he once added to his equations, almost reluctantly, and then called his greatest mistake. But first, an older, quieter warning, from before anyone knew any of this was coming. Long before anyone spoke of dark energy or measured the accelerating sky, a few physicists noticed quietly that the energy of empty space might be a problem. Their early warnings were half forgotten, and it is worth recovering them because they show that the trouble was visible almost as soon as the quantum vacuum was born. The first hint came from Walter Nernst, a German chemist and physicist in 1916. Nernst proposed that empty space might be filled with a kind of radiant energy even when no light was present, an early guess at what we now call zero-point energy. He was reaching toward the right idea decades before quantum field theory existed. But he also saw a difficulty. If space really held such energy, and if that energy behaved like any other, it should have consequences that ought to be visible, and it was not clear where they had gone. The sharper warning came from Wolfgang Pauli, one of the most brilliant and famously exacting physicists of the 20th century, known for a tongue so critical that colleagues dreaded his questions. Sometime in the 1920s or 30s, Pauli did a rough calculation that few people knew about at the time. He took the zero-point energy of the electromagnetic field, decided on a reasonable place to stop counting the smallest waves, and then asked what that energy would do to the universe through gravity. Because energy gravitates, a vacuum full of zero-point energy would curve space, and Pauli worked out how tightly. The answer he found was already absurd, and he put it in a way that has been repeated ever since. If the vacuum held as much energy as this simple estimate suggested, its gravity would curl the whole universe up so tightly that, in his words, it would not even reach to the moon. A universe crushed by the weight of its own empty space, so small you could not fit the Earth and the moon inside it. Pauli knew this was nonsense. The real universe is vast and old, so the energy of the vacuum, whatever it truly was, could not possibly be weighing on space the way the naive calculation demanded. Pauli was careful and honest about it. He understood that the simple sum of zero-point energies was not something to take too seriously as a source of gravity, and he even set the discussion aside rather than press it. He sensed there must be some reason the vacuum's weight did not wreck the cosmos, but he could not say what that reason was. He put the puzzle down and moved on, and for decades so did nearly everyone else. This is the part of the story that the common tellings usually leave out. The vacuum catastrophe is often presented as a modern shock, a surprise sprung on physicists in recent decades. But the seed of it was there in the 1920s and 30s, spotted by first-rate minds like Nernst and Pauli, and then quietly shelved because no one knew what to do with it, and because, without a measured value to compare against, it stayed an abstract worry. It was easier to assume that some future insight would explain the weight of the vacuum away, that the whole thing would cancel to nothing for reasons yet to be discovered. For a long while, assuming the cancellation was the sensible course, perhaps some deep symmetry of nature forced the vacuum energy to be exactly zero. If empty space weighed nothing, there was no catastrophe, and Pauli's absurd tiny universe was just a warning about taking a naive sum too literally. Many physicists, when they thought about it at all, expected the true answer to be a clean zero. That comfortable expectation held until the very end of the 20th century. Then the astronomers looked out at the dying light of distant exploding stars, measured how the universe was expanding, and found that the energy of empty space is not zero after all. To understand why that discovery turned an old, shelved worry into the sharpest problem in physics, we have to bring in Einstein and the term he added to his equations and came to regret. To see why the weight of empty space matters so much, we have to bring in the other great theory of the 20th century, Einstein's theory of gravity, which he called general relativity. Its central idea is simple to state and strange to absorb. Gravity is not a force reaching across space in the old sense. It is the bending of space and time by energy and matter. A heavy object curves the space around it, and other things move along that curve. The Earth circles the Sun because the Sun's mass has shaped the space nearby, and the Earth is rolling along the valley that mass creates. The key word for us is energy. In Einstein's equations, it is not only matter that bends space. Anything carrying energy does, because mass and energy are two faces of the same thing, as his famous relation between them says. Light bends space, heat bends space. and if empty space itself carries energy, then empty space bends space. The vacuum, if it has energy, must gravitate. When Einstein first wrote down his gravity equations in 1915, he soon noticed something that troubled him. The equations, left to themselves, would not permit a static universe. A cosmos full of matter, all pulling on itself by gravity, should either be collapsing inward or flying apart. It could not simply sit still. But in 1917, everyone, Einstein included, believed the universe was static, unchanging on the larger scale. So to hold his universe still, Einstein added a new term to his equations by hand. That term is called the cosmological constant, usually written with the Greek letter lambda. Einstein put it in as a kind of counterweight, a built-in tendency of space to push outward, exactly balancing the inward pull of all the matter, so the universe could rest in perfect, motionless balance. It was an addition of convenience, tuned to give the answer he expected, and he was never fully comfortable with it. Then, in 1929, the astronomer Edwin Hubble showed that the universe is not static at all. Distant galaxies are rushing away from us, and the farther off they are, the faster they flee. The universe is expanding. The Belgian priest and physicist Georges Lemaitre had already worked out that Einstein's equations, without any fudging, naturally predicted exactly such an expansion. There had been no need to force the universe to stand still, because it never was. With the universe now known to expand, Einstein's counterweight seemed pointless, even embarrassing. He had added the cosmological constant to prevent a motion that turned out to be real. He dropped the term, setting lambda to 0, and according to the physicist George Gamow, Einstein later called introducing it the biggest blunder of his life. For the next several decades, most physicists treated the cosmological constant as a mistake best forgotten, an unnecessary term that nature had declined to use. But here is where our two threads reach toward each other, and the reaching is the whole point. Einstein's cosmological constant is, in its effect on the equations, exactly the same as a uniform energy filling all of empty space. A cosmological constant and a vacuum energy density are, mathematically, the same thing wearing two names. Lambda describes a smooth, even push built into space itself, present everywhere, the same in every direction, unchanging from place to place. And that is precisely the character we found for the 0-point energy of the quantum vacuum, an even, directionless energy filling every corner of nothing. So the term Einstein added and then regretted, the counterweight he thought was an idle mistake, turns out to be the natural home for the trembling energy of the quantum fields. If the vacuum carries energy, it acts as a cosmological constant, and if quantum field theory is right about how much energy the vacuum carries, then lambda is not 0, and it is not small, it is enormous. Someone had to notice that these two ideas were the same, and put a number to it. The person who first stated the connection clearly, at the right moment and in a way the physics community could not ignore, was the Soviet physicist Yakov Zeldovich. He was one of the most versatile scientists of his century, a man who worked on everything from the physics of explosions to the structure of the universe, and in the late 1960s he turned his attention to the energy of the vacuum. Zeldovich saw plainly what others had shelved. The 0-point energy of the quantum fields, he argued, cannot simply be ignored once gravity is in the picture, because that energy gravitates, and it acts exactly as a cosmological constant in Einstein's equations. He was the one who joined the two halves of our story out loud, the quantum vacuum on one side and Einstein's lambda on the other, and insisted they were the same physical thing. If the fields tremble, space has a built-in push, and the size of that push is set by how much the fields tremble. Then he did the estimate, and he was honest about the result. Zeldovich did not even use the wildest possible cutoff. He made what he considered a modest, cautious choice about where to stop counting the smallest waves, using a scale tied to the masses of known particles rather than the far tinier Planck length. Even so, the vacuum energy he calculated came out vastly larger than anything the universe could tolerate. larger than the observational limits of his day by dozens of orders of magnitude. In his own papers, he remarked that such an estimate has nothing in common with reality. That phrase is worth holding on to because it captures the strange honesty of this whole problem. Zeldovich was not hiding a failure. He was announcing one. He had taken two of the best established theories in physics, quantum field theory and general relativity, combined them in the most straightforward way, and gotten an answer that was obviously absurdly wrong. The vacuum energy his calculation demanded would have curled the universe up long ago, just as Pauli had warned decades earlier. And yet the universe was plainly still here, large and calm. Zeldovich's contribution was not to solve the problem. He could not solve it, and he knew it. His contribution was to state it precisely and refuse to look away. Where Pauli had sensed a puzzle and set it aside, and where most physicists had assumed some future symmetry would force the vacuum energy to vanish, Zeldovich laid the discrepancy out as a real, quantitative conflict at the heart of physics. The two theories we trust most, taken together, predict a vacuum that should have wrecked the cosmos. He also tried, tentatively, to find a way out. Perhaps he suggested the largest part of the vacuum energy is somehow exactly cancelled by some mechanism, leaving only a small remainder from more subtle effects. It was a hopeful guess, and it pointed in a direction many would later follow. But he had no proof that any such cancellation actually happens, and neither, decades later, does anyone else. With Zeldovich, the vacuum catastrophe stopped being a half-remembered worry from the early quantum days and became a stated problem with a number attached. The energy of empty space, according to our theories, is real, it gravitates, and it is far too large. Something must be holding it down, and no one knew what. For about 20 years after Zeldovich, the problem sat in the background, acknowledged by those who thought about gravity and the quantum together, but not yet at the centre of attention. It took a review article by one of the great theorists of the age to drag it into the full light and give it the name it carries today, along with the blunt verdict that it is the worst prediction in all of physics. In 1989, the physicist Steven Weinberg, one of the architects of the modern theory of particles and a Nobel laureate, published a long review article with a plain title, The Cosmological Constant Problem. It became one of the most cited papers in theoretical physics, and it did for this puzzle what a good map does for a wilderness. It laid out clearly where everything stood, what had been tried, and why nothing worked. Weinberg gathered the strands we have followed. Quantum field theory says the vacuum carries energy. General relativity says that energy gravitates as a cosmological constant. The predicted amount is catastrophically larger than anything observed, and every attempt to explain why the real value is so small had, up to that point, failed. He went through the proposed escapes one by one and showed where each fell short. The paper was not a solution. It was an honest, thorough accounting of a deep failure, written by someone with the standing to make the whole field pay attention. It is worth pausing on how unusual this is. Physics is a science of successes. Its story is usually told as a march of theories that work, predictions confirmed, mysteries closed. The cosmological constant problem is the opposite, a place where our best theories, combined in the most natural way, produce an answer that is not slightly off but wrong beyond all reason. Weinberg's review made it impossible to pretend this was a minor technical wrinkle. It was, he made clear, a crisis sitting quietly at the foundation of physics. Weinberg framed the size of the failure in a way that has been repeated ever since. The energy density that quantum field theory predicts for the vacuum, when you cut the sum off at the Planck scale, is larger than the largest value the universe could possibly tolerate by a factor with roughly 120 zeros after it. Physicists have called it the largest discrepancy between theory and experiment in all of science, and probably the worst theoretical prediction in the history of physics. Those are not the words of critics outside the field. They are the words physicists use about their own best work. Let that number settle, because in a moment we will build it up piece by piece. A factor of 120 zeros is not a near miss. If you're off by that much in estimating the number of atoms in your body, your guess would be wrong by more than the number of atoms in the entire observable universe, many times over. It is not the kind of error you make by using slightly the wrong value for some constant. It is the kind of error that says something fundamental is missing from the picture. And yet, Weinberg was careful to stress, every step that leads to that number is built on physics we trust. Zero-point energy is real, confirmed by the Casimir force we can measure on a bench. The rules of quantum field theory give the electron's magnetism to 12 digits. General relativity has passed every test thrown at it, from the bending of starlight to the ticking of clocks. Each piece is solid. It is only when you put them together and ask about the weight of empty space that the whole edifice produces nonsense. Weinberg also did something bolder in a separate line of work, which we will come to. He argued that if you cannot explain why the vacuum energy is small, perhaps you can at least explain why it is not larger than it is, by asking what values would even allow observers like us to exist. That idea would become one of the most debated in modern physics. But before we weigh those escapes, we should do what Weinberg did and actually build the terrible number ourselves, slowly, so its size is not just a phrase but something you can feel. Let us build the number carefully, the one with 120 zeros, because saying it and feeling it are different things. We will do it in plain words, with no equations, just a careful accounting of scale. Start with what we are comparing. On one side is the amount of vacuum energy that quantum field theory predicts. On the other is the amount the real universe actually contains, which astronomers have now measured. The catastrophe is the ratio between them, how many times larger the prediction is than the reality. Begin with the prediction. To get it, we add up the 0-point trembling of the fields, half a grain for every possible wave, and we have to choose where to stop counting the smallest, most energetic ripples. The natural place is the Planck scale, the distance below which our current physics simply stops making sense, where the quantum nature of gravity itself would take over. That scale is set by combining three fundamental constants: the speed of light, Planck's constant, and the strength of gravity, and it is fantastically small. When you carry the sum down to that scale, the energy packed into every cubic centimetre of empty space comes out to a value so large that words strain to hold it. A thimble of such vacuum would carry more energy than all the stars in all the galaxies we can see. Now the reality. The universe does have some vacuum energy, as we'll see when we reach the discovery of cosmic acceleration. Astronomers have measured it, and it is tiny. Spread across all of space, the real energy of the vacuum amounts, in each cubic centimetre, to something like the energy of a few atoms at rest, an almost unimaginably faint whisper. Empty space really is very nearly empty of energy. The universe is calm precisely because this number is so small. Put the two side by side. The predicted vacuum energy density and the measured one differ by a factor that, written out, is a one followed by roughly 120 zeros. Some ways of counting give a somewhat smaller exponent, depending on where you choose to stop the sum, but even the most cautious versions leave a gap of 50 or 60 zeros, and the straightforward Planck scale estimate lands near 120. There is no reasonable choice of cutoff that brings the two into agreement. The prediction always towers over the measurement by a factor beyond ordinary comprehension. To feel 120 zeros, try this. The number of grains of sand on all the beaches of the Earth is often estimated at around a 1 followed by 18 or 19 zeros. The number of atoms in the observable universe is around a 1 followed by 80 zeros. So the gap between the predicted and measured vacuum energy is larger than the number of atoms in the entire universe, and then larger still by a factor with 40 more zeros on top. It is not a quantity that fits inside anything we can point to. It is simply the largest wrongness in physics. This is the vacuum catastrophe, sometimes called the cosmological constant problem, and now you can see why it earned such heavy words. It is not that the theory is a little imprecise, it is that the most straightforward calculation using physics confirmed 12 digits elsewhere, misses the truth by more than the universe can contain. Faced with a number like that, the natural first thought is that the prediction must simply be meaningless, a sign we are doing the sum wrong. But the disagreement will not go away so easily, because that enormous energy would have real, visible effects. If it were truly there, we would not be here to complain about it. To see why, we have to ask what a universe crushed under its own vacuum would actually look like. It is one thing to say the predicted vacuum energy is a huge number. It is another to see what that energy would actually do to the universe, because the doing is what makes the problem impossible to shrug off. A large number on paper might be a mistake in the arithmetic. A universe torn apart is harder to argue with. Recall that in Einstein's gravity, the energy of the vacuum acts as a cosmological constant, a smooth push or pull built into space itself. The sign of that energy decides which way it pushes. If the vacuum energy is positive, space is driven to expand, and the more energy, the faster and more violently it expands. If the vacuum energy is negative, space is pulled to collapse, faster and harder the larger the energy. Either way, a large vacuum energy means a large effect on the whole of space, everywhere, all the time. Now feed in the predicted amount, the one with 120 zeros. With that much positive vacuum energy, space would fly apart with unimaginable ferocity. Every region would rush away from every other so fast that nothing could ever hold together. Matter could never gather into stars or galaxies, because any two specks of it would be hurled apart before gravity could pull them close. The expansion would be so brutal that a region the size of an atom would be stretched to enormous size in the blink of an eye and go on stretching without end. There would be no structure anywhere, no clumps, no cosmos in any recognizable sense, just a furious, featureless flying apart. With the sign flipped, the picture is just as fatal in the other direction. That much negative vacuum energy would slam space shut, collapsing the entire universe to a point almost as soon as it began. This is the version Pauli reached for when he said the universe would not even reach to the moon. A cosmos crushed by the weight of its own empty space, tiny and short-lived. Either way, the universe the prediction describes is one where nothing like us could ever form. No galaxies, no stars, no planets, no slow billions of years for chemistry to build living things. A universe ruled by the predicted vacuum energy would be over, one way or another, before it could ever hold a single atom in a stable place. And yet, look around. The real universe is 13.8 billion years old, wide and calm, full of galaxies that formed slowly and hold together, stars that burn steadily, planets that circle them for ages. Structure had time to grow, gravity was allowed to do its patient work. The expansion of space is gentle enough that matter could clump into everything we see, including us. The vacuum, whatever energy it truly holds, is not tearing the cosmos apart or crushing it shut. It is barely doing anything at all. This is what turns the vacuum catastrophe from a curiosity into a genuine crisis. The disagreement between theory and observation is not hidden in some hard-to-reach measurement. It is written across the entire sky. The very existence of a stable, structured universe, old enough and calm enough to have produced a person reading these words, is direct evidence that the predicted vacuum energy is not there. If it were, there would be no here. So the enormous number cannot simply be waved away as a meaningless artifact of the calculation. The universe itself is the measurement, and the universe says the vacuum energy is fantastically smaller than predicted, small enough to let a cosmos exist. Something reduces that 120 zero prediction down to a faint whisper, and the way it must be reduced turns out to be even stranger than the size of the error itself. Here is the subtlety that makes the cosmological constant problem so much deeper than a simple case of a wrong number, and it is the part most tellings rush past. The trouble is not only that the predicted vacuum energy is too big, it is that reducing it to the tiny observed value requires a cancellation so precise it defies belief. Think about where the vacuum energy comes from. It is a sum of many contributions. Every field of nature adds its own 0-point trembling. On top of that, various processes in the early universe, phase changes as space cooled, are each expected to shift the vacuum energy by their own large amounts. So the total is a sum of many separate pieces, each one enormous, each one roughly of that catastrophic Planck scale size, some positive and some negative. Now, the observed vacuum energy is not zero. It is tiny, but real, a faint positive whisper. For the huge separate contributions to add up to that whisper, they must very nearly, but not exactly, cancel one another out. The positive pieces and the negative pieces must line up and subtract down to almost nothing, leaving only the faintest remainder. Picture how precise that cancellation has to be. Imagine several people each writing down an enormous number, a figure with 120 digits, chosen independently, some to be added and some subtracted. For the final total to come out not as another huge number, but as a tiny one, all those 120-digit numbers would have to agree with each other, digit for digit, all the way down, until only the very last digit or two failed to match. The first 118 digits would have to cancel exactly, by sheer coincidence, leaving a difference in only the final places. That is what the real universe seems to require. The various large contributions to the vacuum energy, which have no obvious reason to know anything about each other, must cancel to something like 120 decimal places, leaving behind just the faint remainder we observe. In physics, when a quantity has to be adjusted with that kind of fantastic precision to match reality, and there is no known reason forcing the adjustment, we call it fine-tuning, and physicists distrust it deeply. Fine-tuning at the level of 100+ decimal places is not something anyone can accept as mere chance. It cries out for an explanation. This is the real shape of the problem. It is not why is the number wrong. It is why is the number so exquisitely, delicately, almost perfectly cancelled, and yet not perfectly, stopping just short of zero at a value that happens to allow a universe like ours. A perfect cancellation to exactly zero might be explained one day by some deep symmetry, some law forcing the pieces to sum to nothing. But the observed value is not zero. It is small and positive and non-zero, which is somehow worse. A symmetry that forces exact zero would be elegant. A value that is almost, but not quite, zero seems to need a reason that is neither zero nor large, a reason poised on a knife's edge. For most of the 20th century, physicists could at least hope the answer was a clean zero. Perhaps some undiscovered symmetry cancelled the vacuum energy exactly, and the naive prediction was simply a sign we had not yet found that symmetry. Under that hope, the vacuum weighed nothing, and Pauli's absurd tiny universe was just a warning against a careless sum. It was a comforting thought, and it lasted right up until the moment astronomers actually measured the weight of empty space and found it was not zero at all. That measurement came at the very end of the century, from the light of exploding stars, and it changed the problem from a theorist's worry into a hard, observed fact. For most of the 20th century, astronomers assumed the expansion of the universe must be slowing down. It seemed obvious. Space had been flying apart since the beginning, and all the matter in it, pulling on itself by gravity, should be gradually putting on the brakes. The only real question was how fast the slowing was, and whether gravity would one day halt the expansion and pull everything back together, or merely slow it forever. To find out, astronomers needed to measure the expansion not just now, but long ago, and compare. The tool they used was a particular kind of exploding star, a type of supernova known as Type 1a. These explosions happen when a dense stellar cinder called a white dwarf pulls in too much matter and detonates, and they are precious to astronomers for one reason. They all explode with very nearly the same true brightness. That makes them standard candles. If you know how bright a thing truly is, and you measure how bright it looks from Earth, The difference tells you how far away it is, because light dims in a precise way with distance. And because light takes time to travel, seeing a distant supernova means seeing the universe as it was long ago. In the 1990s, two rival teams set out to measure the expansion of the past by finding these exploding stars in very distant galaxies. One was the Supernova Cosmology project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, whose members included Brian Schmidt and Adam Rees. Both teams expected to measure how much the expansion had slowed. They were racing to pin down the deceleration. In 1998, both teams found the opposite of what they expected. The distant supernovae were fainter than they should have been. A far-off exploding star looked dimmer, which meant it was farther away than a merely slowing universe could account for. The only way to make sense of it was that the expansion of the universe had not been slowing down over the last several billion years. It had been speeding up. The universe is expanding faster now than it was in the distant past. Space is not coasting to a stop under gravity. It is accelerating apart. This was a genuine shock, so unexpected that both teams checked and rechecked, hunting for errors before they dared to announce it. But the result held, and it held across both independent groups using different supernovae, which is exactly the kind of agreement that turns a surprise into a discovery. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for it. Now what could make the expansion of the universe speed up? Ordinary matter cannot. Gravity from matter always pulls inward, always tends to slow expansion down. To push space apart faster and faster, you need something with the opposite effect, a form of energy whose gravity repels rather than attracts, spreads smoothly through all of space, pushing everything outward. You need, in other words, a positive energy filling the vacuum. You need exactly the cosmological constant that Einstein added and discarded, and exactly the vacuum energy that quantum field theory predicts. The accelerating universe is the fingerprint of vacuum energy seen at last. Empty space really does carry energy, and that energy really does push space apart, just as the theory said it should in kind, if not in amount. The old hope that the vacuum energy might be exactly zero was gone. The number is not zero, it is real, it is positive, and now it had to be given a name and a size. The energy driving the universe apart needed a name, and the name that stuck is dark energy. The word dark here means only that we cannot see it and do not understand it, not that it is sinister. It is simply the name for whatever fills empty space and pushes the expansion of the universe to accelerate. And when astronomers worked out how much of it there must be, the answer reshaped our whole picture of what the universe is made of. To make the expansion accelerate at the observed rate, dark energy has to make up the majority of the universe's total content. The best measurements, drawn from supernovae, from the faint afterglow of the early universe, and from the way galaxies are spread across the sky, all agree. About 68 to 70% of everything in the universe is this dark energy of empty space. Roughly another 27% is dark matter, a still unidentified kind of matter that clumps and pulls by gravity, but gives off no light. And everything else, all the ordinary matter, every star and planet and cloud of gas, every atom in your body and in all the world you've ever seen, adds up to only about 5% of the whole. Sit with that division for a moment. The stuff we are made of, the stuff that lights the sky and fills the periodic table, is a thin 5% skin on a universe dominated by two things we barely understand. And the largest share of all, the majority of everything, is the energy of empty space itself, the very vacuum energy this whole story has been circling. The trembling of the fields, weighed at last, turns out to be the single biggest ingredient of the cosmos. So the cosmological constant is back, exactly as Einstein first wrote it, though for a reason he never imagined. It is not a fudge to hold the universe still. It is a real energy in the vacuum, driving the universe to expand ever faster. lambda has a measured value now, and dark energy behaving as a cosmological constant fits the observations well. The term Einstein called his greatest blunder appears to describe the dominant feature of the universe. And here is where the two threads of our story finally snap tight against each other, because now we have both numbers. Quantum field theory predicts a vacuum energy. Astronomers have measured the vacuum energy. We can lay them side by side at last. The prediction, from the trembling of the fields cut off at the Planck scale, is the catastrophic figure with 120 zeros. The measurement, from the accelerating sky, is the faint whisper, a few atoms worth of energy per cubic centimetre of space. They do not match. They miss each other by that same staggering factor we built up earlier. The theory that gets the electron's magnetism right to 12 digits overshoots the actual energy of empty space by more than the number of atoms in the universe, many times over. Before 1998, a hopeful physicist could imagine that the true vacuum energy was exactly zero, cancelled by some symmetry we had not yet found, and that the naive prediction was simply meaningless. That escape is now closed. The vacuum energy is measured. It is not zero. It is just fantastically precisely smaller than the theory says. This is why the problem is called the mistake physicists cannot ignore. It is no longer an abstract mismatch that might dissolve on closer inspection. It is a hard number on both sides, prediction and measurement, and the two refuse to meet. And as we look closer, the single problem splits into two problems, each hard in its own way. The cosmological constant problem is often spoken of as one puzzle, but it is cleaner to see it as two, because they call for different kinds of answers, and it helps to keep them apart. Physicists sometimes call them the old problem and the new problem. The old problem is the one we have built up all along. Why is the vacuum energy so small? Quantum field theory predicts an enormous value, and the universe shows a tiny one. Something must suppress the huge predicted energy down by that factor, with 120 zeros. For decades, the cleanest imaginable answer to this was zero. If some deep symmetry of nature forced the vacuum energy to cancel to exactly nothing, then the smallness would be explained in the most satisfying way, not small by luck, but zero by law. Much of the effort to solve the old problem was a search for such a symmetry, a reason the pieces must sum precisely to zero. Then came 1998, and with it the new problem, which is in some ways harder. The vacuum energy is not zero. It is small, but real and positive. So now a symmetry that forces exact cancellation to zero is not enough, and might even be too much, because it would give zero when the answer is a little more than zero. We need to explain not why the vacuum energy vanishes, but why it sits at one particular tiny, non-zero value, poised delicately between the crushing largeness the theory predicts and the clean zero a symmetry might provide. The new problem has a second, stranger face, sometimes called the coincidence problem, and it is worth seeing on its own. The energy of matter in the universe thins out as space expands, because the same matter is spread over ever more room. But the energy of the vacuum does not thin out. It is a property of space itself, so as new space appears in the expansion, it comes with the same vacuum energy per volume as always. This means that early in cosmic history, matter dominated utterly, and the vacuum energy was negligible by comparison. Far in the future, matter will be so thinly spread that vacuum energy will dominate almost completely. These two, matter density and vacuum energy density, cross over each other only briefly, in one passing era. And here is the coincidence. We happen to live near that crossover, in the relatively brief span when matter and dark energy are of roughly comparable importance, when the universe is just tipping from the matter-ruled past into the vacuum-ruled future. Out of all the vast stretch of cosmic time, we find ourselves at the rare moment when the two are close to balance. That could be pure chance. Or it could be a clue that we are missing something about how the vacuum energy relates to the rest of the universe. So the single phrase, the cosmological constant problem, actually holds three tangled questions. Why is the vacuum energy not enormous, as the theory demands? Why is it not exactly zero, as a symmetry might enforce? And why does its tiny value happen to be comparable to the density of matter right now, in our particular cosmic moment? Each is a real puzzle, and none has a settled answer. Faced with all this, physicists have not been idle. Over the decades, they have proposed several serious ideas for taming the vacuum energy, each ingenious, each with a following, and so far each falling short of a full solution. The first and most elegant of these, the one that came closest to making the huge number cancel by a beautiful law of nature, is a symmetry called supersymmetry. The most beautiful proposed cure for the vacuum catastrophe is an idea called supersymmetry, and understanding why it almost works and why it does not quite tells you a great deal about the whole problem. It begins with a fact about how different particles contribute to the vacuum energy. The particles of nature come in two broad families. There are the particles that make up matter, such as electrons and the building blocks of protons and neutrons, called fermions, and there are the particles that carry forces, such as the photon of light, called bosons. When you add up their 0-point trembling in the vacuum, something interesting happens. Fermions and bosons contribute with opposite signs. The trembling of matter particles pushes the vacuum energy one way, and the trembling of force particles pushes it the other way. One adds, the other subtracts. Supersymmetry is the proposal that this opposition is not an accident but a deep law. It says that for every kind of boson there is a matching fermion, and for every fermion a matching boson, paired up so their properties correspond exactly. If that pairing were perfect, then for every positive contribution to the vacuum energy from one partner, there would be an equal and opposite negative contribution from the other. They would cancel, partner by partner, all the way up the enormous sum. The catastrophic vacuum energy would subtract itself away to exactly zero, not by luck, but because the symmetry between the two families demands it. This is exactly the kind of answer physicists dreamed of for the old problem. It is a genuine law of nature that forces the huge cancellation, cleanly and beautifully, rather than requiring 120 digits to line up by coincidence. For a while, supersymmetry looked like it might be the reason empty space does not crush the universe. If nature is supersymmetric, the vacuum energy is naturally zero. But there is a hard catch, and it is fatal to the simple version. If supersymmetry were exact, then every particle we know would have a partner of the same mass. The electron would have a partner just as light as itself, easy to find. These partners do not exist at the mass's exact supersymmetry requires. We have looked in our most powerful particle colliders and found none of them. So if supersymmetry is a real feature of nature at all, it must be broken. The partners, if they exist, must be much heavier than their familiar counterparts, heavy enough to have escaped detection so far. And a broken symmetry means an imperfect cancellation. If the partners have different masses from the particles we know, then their opposite contributions to the vacuum energy no longer match exactly. They cancel most of the way, but not all the way, leaving a remainder. And that remainder, set by the scale at which supersymmetry breaks, is still enormous compared to the observed vacuum energy. The best case, even granting supersymmetry, still overshoots the measured value by something like 50 or 60 orders of magnitude. The beautiful cancellation reduces the catastrophe, but it does not remove it. So supersymmetry stands as a lesson in miniature for the whole problem. It offers exactly the kind of elegant, law-driven cancellation we would want. It cancels most of the terrible number, and then it stops short, leaving a gap still far too large to explain what we see. Nature, it seems, is either not supersymmetric in this simple way, or supersymmetric in some more subtle fashion that does not solve the vacuum energy after all. When a beautiful mechanism falls short, some physicists turn to a very different kind of explanation, one that does not try to force the number to a value at all, but instead asks whether the number could be almost anything, and we simply live where it allows us to. When elegant mechanisms fail, some physicists reach for an idea of a completely different flavour, one that many find unsatisfying, and some find the only honest option left. It is called the anthropic argument, and Steven Weinberg gave it its sharpest form, in fact predicting roughly the value of dark energy years before it was measured. The reasoning runs like this. Suppose the vacuum energy is not fixed by any law to a single value. Suppose instead that it could, in principle, take almost any value, and that its actual value is in some sense random, set by conditions we cannot predict. Then most possible values would be catastrophic, the huge positive or negative numbers the theory naively predicts, and in a universe with such a value, no galaxies, stars, or observers could ever form. Only in the rare case where the vacuum energy happens to be very small could a universe hold together long enough to grow structure and produce living things able to measure it. If that is so, then we should not be surprised to find ourselves in a universe with a tiny vacuum energy, even if such values are rare, because those are the only universes where anyone exists to look. A universe with a catastrophic value has no astronomers in it. The very fact that we are here to ask the question filters the possibilities, selecting out the rare, life-permitting values from the vast majority that are lethal. Weinberg made this concrete before the discovery of dark energy. He reasoned that if the vacuum energy were much larger than a certain amount, the universe would fly apart too fast for galaxies to form, and there would be no place for observers. So he argued that the vacuum energy, if it is non-zero at all, should be no larger than roughly the amount that still allows galaxies to assemble. When dark energy was measured in 1998, its value fell within the range Weinberg had marked out, a tiny, non-zero value, right about where it would need to be to permit a universe with structure in it. For many, this was a striking success. For others, it was uncomfortably close to explaining a number by noting that we are here to see it. This kind of reasoning only carries weight if there really are many universes, or many regions, with different values of the vacuum energy, so that ours can be the rare hospitable one among a great many. And modern theoretical physics does offer a setting where that might be true. String theory, one of the leading attempts to unite gravity with the quantum world, appears to allow an almost unimaginable number of possible vacuum states, each with its own value of the vacuum energy. The physicist Leonard Susskind called this vast range of possibilities the landscape. If our universe is one bubble among a staggering multitude, each with a different vacuum energy, then somewhere in that multitude are the rare bubbles calm enough for observers, and of course we find ourselves in one of them. Many physicists dislike this deeply. It feels less like solving the problem than declaring it unsolvable, trading a hard calculation for an appeal to universes we can never see or test. Others argue it may simply be how nature is, whether we like it or not. The honest position is that the anthropic argument is not confirmed and not refuted. It is a real possibility that many find unsatisfying and no one has been able to rule out. And even setting the vacuum energy aside, there is another field whose contribution deepens the whole puzzle, one we have very good reason to believe is real because we found its particle. That is the Higgs field. There is one more contributor to the vacuum energy that we should bring in, because it is not speculative in the least. It comes from a field we now know exists, whose discovery was one of the great triumphs of recent physics. That is the Higgs field. The Higgs field fills all of space, much like the other fields we have met, but it has an unusual feature. Its lowest energy state, its version of the calm vacuum, is not one where the field sits at zero. Instead, the Higgs field settles at a value that is switched on everywhere, a non-zero level that pervades all of space evenly. Particles moving through this ever-present field interact with it, and that interaction is what gives many of them their mass. An electron has mass because it is, in a sense, wading through the Higgs field as it moves. Without the field switched on, the familiar particles would be massless, and the world could not exist as it does. For decades, the Higgs field was a prediction, proposed in the 1960s by Peter Higgs and several others, to explain how particles acquire mass. Then, in 2012, experiments at the Large Hadron Collider, the enormous particle accelerator beneath the border of France and Switzerland, found the particle associated with the field, the Higgs boson, the ripple in the Higgs field. Its discovery confirmed that the field is real and switched on throughout space, exactly as the theory required. Peter Higgs and François Englert received the Nobel Prize for the idea the following year. Now here is why this matters for the weight of empty space. A field that is switched on everywhere, sitting at a non-zero value, carries energy in that switched on state. The Higgs field, resting in its true vacuum, contributes its own large amount to the energy of empty space. And when physicists estimate how much, they find yet another enormous contribution, far larger than the tiny observed vacuum energy, though not as large as the full Planck scale figure. The Higgs field alone, by settling into its everyday state, adds a term to the vacuum energy that overshoots the measured value by dozens of orders of magnitude. This makes the fine-tuning puzzle even sharper, because now we have a concrete confirmed source of large vacuum energy that must be cancelled. It is not just the abstract sum of zero-point trembling. The Higgs field, which we've found and studied, throws in its own huge contribution, and that contribution too must be almost perfectly subtracted away by something to leave the faint remainder we observe. The various large pieces, the zero-point energies of the fields, the energy of the switched-on Higgs, the shifts from the early universe's phase changes, all have to conspire to cancel down to that 120 decimal place whisper. Nothing in our theories tells these separate contributions to coordinate. The Higgs field knows nothing of the zero-point trembling of the photon field. The phase changes of the early universe know nothing of the value dark energy would need today. Yet their vast independent contributions must sum to almost exactly nothing, missing zero by the tiniest sliver and landing on the one small value that lets a universe like ours exist. Stated this way, the problem feels less like a gap in a calculation and more like a deep hint that we are missing something fundamental about how energy, gravity, and empty space fit together. And just as physicists had grown used to the idea that dark energy is at least a fixed cosmological constant, a single, unchanging number, however mysterious, new observations have begun to suggest that even this may not be true. The constant may not be constant, and that is the freshest turn in the whole story. For 25 years after the discovery of cosmic acceleration, the simplest picture held up well. Dark energy behaved like a true cosmological constant, a fixed energy of the vacuum, the same in every era, an unchanging property of space itself. This simple model, combined with dark matter, became the standard description of the universe, and it fit the data remarkably well. However mysterious dark energy was, at least it seemed to be constant. That assumption is now being tested with unprecedented care, and the early results are unsettling it. The instrument doing the testing is called the Dark Energy Spectroscopic Instrument, or DESI, mounted on a telescope in Arizona. It is building the largest three-dimensional map of the universe ever made, measuring the positions of millions of galaxies and bright distant objects stretching back billions of years. By tracking how matter is spread across cosmic history, DESI can measure not just how fast the universe is expanding, but how the strength of dark energy has changed over time. If dark energy is a true cosmological constant, its push should have been the same in the distant past as it is today. DESI can check this. And in its first major results, released in 2024 and strengthened in a larger analysis in 2025, the collaboration found something that made cosmologists sit up. Taken on their own, DESI's measurements are still consistent with a constant. But when combined with other data, the light left over from the early universe, the exploding stars of supernova surveys, and the subtle bending of light by gravity, a different picture begins to favour itself. The combined data hint that dark energy may not be constant after all. Its strength may have been slightly different in the past and may be gradually weakening now. The DESI team has been careful, and so should we. This is a hint, not a proven fact. The evidence is suggestive, not yet at the level of certainty that physicists demand before they overturn a standard model. One of the survey's leaders described the situation by saying that the simplest explanation for what they see appears to be shifting, and that evolving dark energy looks increasingly promising as a better fit. But he and his colleagues stress that more data are needed, and Deci continues to gather them. The result could firm up into a discovery, or it could fade as the measurements improve. Both outcomes are live. Still, notice why even the hint is so important, and why it belongs in this story. If dark energy is truly constant, it fits neatly into Einstein's equations as the cosmological constant, the vacuum energy we've been chasing, and the whole problem is the one we've described, a fixed number that is fantastically too small compared to the prediction. But if dark energy is changing over time, then it cannot simply be the energy of the vacuum, because vacuum energy, being a property of space itself, does not change as the universe evolves. A dark energy that weakens or shifts would have to be something else, something more dynamic than a constant, some new field or influence filling the universe. That would transform the problem. It would mean the thing driving cosmic acceleration is not merely the static vacuum energy that quantum field theory predicts badly, but a moving, evolving presence with its own behaviour and its own unknown physics. The mistake physicists cannot ignore would grow a new dimension. Not only is the vacuum energy the wrong size, but the dark energy we measure might not be vacuum energy at all, in the pure sense, and might be changing before our eyes. This is why the problem is sharper now than ever. The freshest data are pointing not toward a resolution, but toward a deeper mystery. If the constant is not constant, physics needs a new idea for what dark energy is, and the leading candidate carries its own strange name. If dark energy is changing over time, as the newest hints suggest it might be, then it cannot be the simple energy of the vacuum, and physicists need a different kind of explanation. The leading candidate has a name borrowed from old philosophy. It is called quintessence, after the ancient idea of a fifth element beyond earth, water, air and fire, a subtle essence filling the heavens. Quintessence in modern physics means a new field spread through all of space, something like the Higgs field or the electromagnetic field, but with a special property. Its energy can change slowly over the history of the universe. Rather than a fixed cosmological constant, unchanging from the beginning of time, quintessence would be a field that rolls gradually from one value to another over billions of years, and as it rolls, the strength of its outward push changes with it. Early in cosmic history it might have pushed one way, and today, having evolved, it might push a little differently. That is exactly the kind of behaviour the Deci hints would require, a dark energy that is not quite constant but drifting. The appeal of quintessence is that it could in principle match a changing dark energy. The difficulty is that it does not by itself solve the original problem. It replaces a mysterious constant with a mysterious field, and that field still has to be extraordinarily gentle and extraordinarily light, tuned to roll at just the right slow pace to match what we see. Introducing quintessence trades one fine-tuning for another, and it adds a new ingredient to the universe whose deeper origin is unknown. It is a serious idea, actively studied, but not a finished answer. What makes the possibility of evolving dark energy so gripping is what it would mean for the future of the universe, because the fate of everything hangs on how dark energy behaves. If dark energy is a true fixed cosmological constant, the future is fairly clear. The universe will expand faster and faster forever, galaxies will race apart until distant ones vanish from view, and the cosmos will grow ever colder, darker and emptier, coasting into a long, quiet dimming. But if dark energy is dynamic, if it can change, then that future is not fixed. Should the push of dark energy weaken enough over time, the acceleration could slow, and the runaway expansion might gentle into something calmer. In some versions, if dark energy were to reverse and pull inward, the expansion could one day halt and turn around, and the universe could eventually contract again. The difference between an eternal cold expansion and a distant reversal comes down entirely to whether the dark energy is constant or evolving, and by how much. The measurements Deci and its successors are making are, in a real sense, measurements of the fate of everything. So the freshest chapter of this story is being written right now, in the data streaming from telescopes mapping the sky. We do not yet know whether dark energy is a fixed vacuum energy or an evolving field. We do not know whether the universe faces an endless dimming or some slower, stranger fate. And we still do not know why the energy of empty space, whatever its true nature, is so many orders of magnitude smaller than our best theory demands. That is a great deal of not knowing, gathered around one of the most basic questions there is: what fills the emptiness? It would be easy to feel that so much uncertainty is a failure, a sign that physics has lost its way. It is worth pausing before we close to see why the opposite is true, why a well-posed, unsolved problem of this kind is one of the most valuable things a science can possess. It is worth being clear and calm about where all of this leaves us, because the honest answer is that the cosmological constant problem is unsolved. No one knows why the energy of empty space is so small. The elegant cancellation of supersymmetry falls short. The anthropic argument, resting on universes we cannot see, satisfies some and troubles many. Quintessence trades one puzzle for another. Every proposed answer either fails to close the gap or buys progress at a price most physicists are reluctant to pay. After a century of work, from Nernst and Pauli through Zeldovich and Weinberg to the astronomers mapping the sky today, the mistake still stands. It would be easy to hear that as bad news, as a defeat. It is not, and it helps to understand why. In science, a sharp, well-defined problem that resists every attempt at solution is not a sign of failure. It is a sign that something important is waiting to be found. The gap between prediction and reality is not vague or fuzzy. It is precise. Our best theory of the small quantum field theory gives a definite answer. Our best theory of the large general relativity tells us exactly what that answer should do to the universe. And the universe plainly disagrees by a specific, enormous, measured amount. That kind of clean contradiction between two great theories is exactly where new physics has come from before. Think of how earlier crises resolved. The ultraviolet catastrophe, the absurd prediction that hot objects should blaze with infinite energy, was not a dead end. It forced Planck to the quantum, and the quantum remade physics. The strange behaviour of light and motion that troubled physicists at the turn of the last century forced Einstein to relativity. In each case, a place where the old theories gave a clearly wrong answer turned out to be the doorway to a deeper one. The vacuum catastrophe may be a doorway of the same kind, a sign that our understanding of gravity, or of the quantum, or of both together, is incomplete in some way we have not yet grasped. What the problem tells us plainly is that we do not yet know how to combine the quantum world and gravity. The vacuum energy sits exactly at the seam between them. Quantum field theory describes the trembling fields. General relativity describes how energy curves space. And when we ask the two to work together on the energy of empty space, they produce nonsense. That is a strong hint that the true, unified theory of quantum gravity, which physicists have sought for decades, will have something essential to say about why the vacuum weighs what it does. The mistake is a signpost pointing at the missing piece. There is also something bracing in the honesty of it. Physics could have quietly ignored this problem, buried the huge number in a redefinition and looked away, as many were tempted to do for years. Instead, the field states it plainly, calls it the worst prediction in the history of physics, and keeps working on it in full view. That willingness to name a failure squarely, to hold it up rather than hide it, is part of what makes the science trustworthy. A field that admits its deepest mistake is a field you can believe when it claims its triumphs. So we stand in an honest place. We know empty space carries energy, we have weighed that energy in the laboratory and in the sky, and we know our best theory gets its total spectacularly wrong. We do not know why, and that unanswered question, precise and stubborn, is one of the clearest views we have of the edge of human knowledge, the place where the next great idea will have to arrive. Which brings us back at the end to the empty room where we began. Return to the room where we started and to the empty space between you and the far wall. When we began, that space looked like nothing, a mere gap, absence itself. We can see it differently now. That emptiness is filled with the fields of nature, trembling in their lowest state, never still, humming with zero-point energy and frothing with virtual particles that flicker in and out, too fast to catch. The nothing around you is one of the busiest things there is. The question the title asked was simple. What is the quantum field mistake physicists cannot ignore? Here it is, in the plainest words. Our best theory of the small says empty space should be heavy beyond imagining, so heavy its gravity would have crushed or shredded the universe long ago. The real universe is calm and light and old. The theory overshoots the true weight of empty space by a factor, with roughly 120 zeros, the largest gap between prediction and reality anywhere in science. That is the mistake. Empty space weighs almost nothing, and no one knows why it does not weigh everything. We can say what we are sure of because it is a great deal. Empty space carries energy, and we have measured its push between two plates on a laboratory bench. That energy fills the universe and drives it to expand ever faster, which we have seen in the fading light of distant exploding stars. It makes up the majority of everything there is, dwarfing all the matter of all the stars and worlds, and its value is fantastically precisely smaller than our deepest theory demands, tuned somehow to the faint whisper that lets galaxies form and lets us exist. Every one of those statements is built on solid measurement. We can also say plainly what we do not know, because that is the honest part. We do not know why the vacuum energy is so small. We do not know what cancels the huge predicted value down to nearly nothing, nor why the cancellation stops just short of zero. We do not yet know whether dark energy is a fixed constant or something evolving over time, and the newest maps of the sky are only beginning to tell us. And underneath it all, we do not know how to fit the quantum world and gravity together, which is the seam where this whole problem lives. Sit for a moment with what that means for you. In your room, on your world, you're made of the 5% of the universe that is ordinary matter, a thin, bright skin on a cosmos ruled by dark matter and dark energy. The very stuff you are built from is the rare, visible exception, and the emptiness you move through, the air your hand parts as you reach across the table, is quietly filled with the largest and least understood ingredient of all, the energy of the vacuum, weighing on space, pushing the whole universe apart, and doing it so gently that a person could live an entire life and never suspect it was there. That is the strange gift of this problem. It takes the most ordinary thing imaginable, the empty space in front of your face, and shows that it holds one of the deepest unsolved mysteries in all of physics. The next great theory, whenever it comes and whoever finds it, will have to explain the weight of nothing. Until then, we get to live inside the question, in a calm, wide universe that, by every naive reckoning, should not be calm or wide at all. Look at the empty space around you once more. It is not empty, it is not simple, and it is not finished being understood. It is the emptiness that lets everything else exist, and the puzzle of its lightness is one of the truest edges we have found of how much is still left to learn.